Hey there, we are going to be doing our last lecture for BI 232. We're finishing up respiratory system. We're going to be looking at mechanics of breathing and also some gas exchange stuff. So let's go ahead and get started. I am going to... we just ended on page 10 there, and you can see where we were. Move this down just a little bit so it'll fit in better. Okay, so we were talking about serous membranes, the parietal membranes, and one of the things we said at the very end is that we have this tight suction between the visceral pleura and the parietal pleura because of the serous fluid, and this actually becomes really important when we talk about mechanics of breathing. So let's go into that right now. So we need to look at how pressure changes in the thoracic cavity as compared to the outside world, what we call atmospheric pressure. So now we can measure pressure, just like we measure blood pressure, we can measure pressure of gas out in the world. And so atmospheric pressure is 760 millimeters of mercury at sea level. We're close enough to sea level where we can just go ahead and use that as our value. And this is basically saying all of the pressure that's being pushed on your skin right now from the atmosphere that we're in. And you don't notice this pressure. This pressure doesn't feel unusual to you because it's typical. However, pressure will change slightly inside, and that will help us breathe correctly. So let's go ahead and talk about how that's going to happen. So we want to look at intrapulmonary pressure, intra-alveolar pressure. All right, this is the pressure inside the lungs in the alveoli. And now this is obviously in a state of flux due to atmospheric changes, but it always equalizes with atmospheric pressure. And that's because our lungs are basically, the inside of our lungs is connected directly to the outside of our body. So if you just stand there and you just open your mouth, you immediately, and you don't move at all, you'll immediately change the pressure, whatever your pressure of your lungs would be, it'll immediately go to the outside pressure because that pressure is huge and vast, and any little change you act on it is so small it will not be noticed, but any change, it can act on changes inside of your lungs quite easily. So generally it's in a constant state of flux, but it always equalizes with atmospheric pressure. And we call this a dynamic equilibrium. There's small little changes all the time as pressure outside goes up and down, but we'll always equalize with the outside. Okay, now we also have intrapleural pressure, and this was the pressure that we were talking about last time, and the pressure that's right here, and it is in the pressure that is being made in between the lung and the wall, the thoracic wall. And that pressure is a negative pressure, and that's what's giving the suction. So the pressure is just lower than the 760. And so what really happens is the 760 is pushing on the walls because it's greater than 756. So as it pushes on those walls there, it holds the lung tightly up against the wall. Another way you can think of it is this is a partial vacuum, and so that vacuum, because it has less pressure, things are sucked towards that vacuum, and this, either way you think about it, that's fine. They both are correct. So let's look at that a little bit more here. So intrapleural or interthoracic pressure is the pressure between the parietal and visceral pleura, and it's always subatmospheric by about 4 millimeters of mercury, which gives it a negative pressure. So one way you can write that is you can say it's negative 4 millimeters of mercury, or the pressure is 756 millimeters of mercury, right? Both of those basically say the same thing. Now, there are two factors that pull the lungs from the thoracic wall, meaning that this negative pressure is holding the lungs against the wall, but there are two factors that want the lungs to collapse on themselves. And one of those is the natural recoil of the lungs. Remember that we said that there was a lot of elastic tissue around the different alveoli and the different respiratory bronchioles. That's what's causing this natural recoil of the lungs. All of that elastic tissue kind of adds up to causing the lungs to want to be smaller. They're stretched slightly and they want to go back to their original shape. The other thing is what we were talking about that surface tension that's inside the alveoli. The fluid that's there, that we like being there because it helps us diffuse gases better, makes the alveoli want to collapse. And if the alveoli collapse, then of course the lungs would get smaller. But remember, we have our surfactant, and the surfactant helps prevent this. So the surfactant is going to help that not happen. So those two factors go against the negative pressure. And that negative pressure is called surface tension adhesion force, or negative pressure. Okay? Now, let's take some of those ideas and talk about how we breathe. And you saw a little example of the bell jar experiment in lab this past week. And so hopefully you can kind of think about that and about the pressure changes as I talk through this. Okay? So first off, Boyle's law of physics, it says volume changes lead to pressure changes, which lead to flow of gases to equalize the pressure. So an easy way to think about this is if something's at high pressure and something's at low pressure, the thing that is at high pressure will want to move to the lower pressure to equalize out. Okay, and this is similar to how things that are at high pressure, at our high concentration, will want to move by diffusion to low concentration. Or water is, there's a lot of water in one place, it'll move by osmosis to where there's less water. So pressure changes are very similar. High pressures always go to low pressures, if they can. Okay, so let's keep that in mind as we talk about inspiration and exhalation. So inspiration or inhalation, breathing in, we have to do a couple things. So one thing we have to do is we have to expand the lungs. When we expand the lungs, volume increases, right? Because the diaphragm will go down and that will make more space. And if the space increases, then the three-dimensional space is volume, it will increase. If the space increases, the gases that are in there have more room to move about, have less time hitting against the wall, and therefore the pressure in that space is less, right? Just as if we were all in a classroom and we had 30 people in a small classroom and we were all right next to each other, the pressure would be high. We'd be very near each other. If we were all walking around, we'd be bumping into each other or having to move out of the way. And if I could magically make that room a lot larger, but keep the number of people in the room, our pressure would go down, right? If we were moving around, we'd have plenty of room to get around each other. No problem, pressure levels would drop. So if we expand our lungs, volume increases, and inside the lungs, intrapulmonary pressure will decrease. So when we expand the lungs, the thoracic cavity will decrease by about 1 to 3 millimeters of mercury. Now, I have up here somewhere this. All right. So these are the pressures. This is that same thing we had before. And now if we look at this here, all right, normally, this is talking about a problem, but we can look at this. Normally, there's a -4 pressure here, all right? Actually, I don't know if maybe I can go back and use the original. I don't want to get to that yet. Okay, so if we change this intrapulmonary pressure down 3 to 4, it is at 757, 756, right? Inside here. But outside in the atmosphere, it's 760. And gas will want to move from high to low. So there's more oxygen, gases in general out here. There's less inside. Therefore, gas will move through and fill the lung. So if we make more space, we can go ahead and have that process happen. Okay, so let's go back to our notes now. So how do we expand? We do it by the diaphragm contracting, right? and we have external intercostal muscles contract, and those elevate the ribs and push the sternum forward, and that kind of expands in multiple directions. So the volume goes up. That's what makes this pressure go down, and that's what causes the air outside, which is at higher pressure, to rush in to fill the lower pressure area. Okay? Now, this is what's occurred when we normally take a deep breath in. You take a deep breath right now. You take a deep breath. What you've done is you've dropped your diaphragm. You might have felt your chest rise up a little. You increased pressure, and as you did that, air was rushing in. You didn't suck air in, air just went in because of the pressure differences. Now, there's different terms, and these different terms here are the different breathing terms. This is more a clinical thing, and U means true, so eupnea is normal, quiet breathing. Apnea is sensation of breathing, like someone has sleep apnea. Sometimes they stop breathing while they're sleeping. Dyspnea is the difficult or painful breathing, and tachypnea is the rapid breathing. Inspiration is active, and this is because it's initiated by muscle contraction, and things that are active need ATP, right? So this is something that we have to generate ATP in order to move our muscles to allow air in. Now, we also can force inspiration. If I say, take a deep, deep breath right now, and you go, you do that, what you might notice when you take a really deep breath is that you're going to use other muscles to try to cause that to happen. Your neck might tighten a little bit, so your sternocleidomastoid, your scalenes, your pectorals, even your erector spinae muscles may all actively work to happen. This is more of a conscious inspiration. Regular inspiration is going to occur passively. Up until I started to ask you to breathe, you've been breathing just fine throughout the entire talk, the 10 minutes before. So forced inspiration is conscious, and we're using other skeletal muscles to kind of help this, all right? So it uses accessory muscles of inspiration, all right, like that. Now, expiration. Expiration or exhalation is due to pressure gradients also, but it's passive. And so that is important. We don't need to do anything. We don't need to contract muscles to just normally expire. What we do is we have a higher pressure in the lungs and that then out in the atmosphere outside. So because the thoracic cage has a lot of air in it, carbon dioxide is loading into the cage for exhaling, and we relax our muscles, all right? So when the inspiratory muscles relax, the thoracic cage will go back to its normal size. So if we decrease the cage size, volume goes down, but the pressure increases, right? So remember that room I was talking about that 30 of us were in. If I had a larger room and we were all moving around in it, and I could magically make the walls start closing in on us, we would start to feel the pressure as we are pushing, we're bumping against each other, we're hitting the walls, pressure would go up. So if we had a door open in that room and we started pushing on these walls, pressure would go up, and some of us would, if we were just randomly moving around, would bounce out the door. We would go out into the hallway where there's lower pressure, and that's exactly what happens. When the muscles relax and the thoracic cage decreases, it compresses the lungs, increasing the alveoli pressure about 1 to 3, and this causes the gas to be expelled. So generally, that interpulmonary pressure for a short period of time is 763 until enough gas leaves and we get down to 760 again, and now we're equal with the original, the external atmospheric pressure. Now, we can also force expire. Right now, if I say, okay, exhale a deep breath, you could just go, or if you blow out like you're blowing out candles, you're force expiring, right? This is an active process because you can even feel that you are contracting muscles, all right? And you're causing the abdominal visceral organs to push the diaphragm up. So that is an expiration where we do use ATP, where we use energy to get air out. But we don't need to normally. If you inhale and that's an active process, then all you have to do is relax your muscles and pressure will build and gases will leave. All right, this last thing, this lung collapse one, would occur if intrapleural pressure was not maintained at a negative pressure. And that was that picture that I was showing you that I kind of didn't want to bring up right away. Oh, did we lose my... All right, we'll go back. Let's see if it'll pop up. If you're out of the book for more than a few minutes, it takes you out. See where it takes us. Okay, yeah, so if we look here, let's say someone has a knife wound, a knife puncture to the thoracic cage, and it enters in through the wall and goes into the pleural cavity. What you've done is you've made a space that out here is 760 millimeters of mercury. This is supposed to be -4 at 756. But now you've made a space. There's an actual gap between. Because of that gap, okay, here, or you can even do it this way, a spontaneous ruptured visceral pleura, there's now a gap from this and here. So what happens is there's a higher pressure here, 760, than in here, 756. There's a higher pressure here, 760 to 763, than here, 756. So guess what? Air rushes into that cavity, and that causes the lung to deflate because we create air here. That suction can't exist anymore, and the lung collapses. So then what we need to do is we need to change the pressure and get the lung to stretch back out. We need to repair the problem and then push the lung, inflate the lung back, and so it will reattach itself to using the negative pressure. All right, so the respiratory volumes and capacities I'm not going to cover because we cover those in lab, so we're not going to ask questions about them on the lecture exam. I will say one thing though, just to be consistent. We are talking about the conducting zone where no gas exchange occurs. There's always some air left there, right? There's air connecting what's in your lungs to the outside world, and about 150 of the total 500 tidal volume is actually in the conducting zone, leaving about 350 inside the respiratory zone. So that's kind of interesting. That's the only thing I wanted to really comment on that. All right, now let's talk about gas exchange for a minute, and then we're going to go into how we transport gases also. So gas exchange. We had talked about the different types of respiration earlier, and let's go back and refresh our memory. So external respiration is the exchange of oxygen and carbon dioxide between the alveoli of the lungs and the pulmonary capillaries. So from the outside world into our blood via the lungs, right? And the exchange of CO2 and O2 between those is external respiration. Now, atmospheric pressure, remember, which is 760, right? We'll put that back in here again so you kind of remember. 760 millimeters mercury. One thing I didn't say about it is it's the sum of all partial pressures in that gas, okay? So air has 760, but each gas that's in the mixture of air that's outside of us has a different pressure. So if you look here, inspired air is 160 millimeters of mercury of oxygen and a very tiny amount of carbon dioxide. Okay? Now, those two add barely up to anything. They don't even get anywhere near 760. There are other gases in the environment. Nitrogen gas is an inert gas that's between all of us right now that we don't inhale or exhale in any large amounts, but it's there as well, and that makes up for the bulk of the atmospheric pressure. And the thing that's kind of cool about these different pressures is, and this is a thing called partial pressure, and I'm actually going to talk about it down here, and then we'll come back up, is that each gas in the mixture exerts its own pressure as if all other gases weren't present. So oxygen will move down its own concentration gradient or pressure gradient from high to low pressure regardless of what the other gases are doing. Okay? So if you have 100 and, what did I just say? 160 outside, and there's only 104 in the lungs, oxygen will want to go into the lungs. If there's only 104 in the lungs and the blood entering the capillaries only has 40, oxygen will want to move from the lungs into these capillaries because this number is higher. So you don't need to necessarily memorize the numbers too much. What you really want to know is the direction of movement of things due to the pressure. So let's look at that a little bit. So that's what I just was saying here. The oxygen pressure, partial pressure, the P in front of the O2 is partial. In alveoli is 104 millimeters of mercury. And the capillaries, it's only 40. So we know that we always go from high to low. So therefore, oxygen diffuses from the alveoli into the deoxygenated blood until we get to about an equilibrium. So we keep loading until the blood is about 104 millimeters of mercury. Okay? So that's important. And that's how the oxygen just on its own, without us using any energy, just loads our blood. Now, think of the carbon dioxide can do the opposite. So it's arriving, we have deoxygenated blood coming into the lungs, and so there's 45 millimeters of mercury of pressure of carbon dioxide in the blood. The alveoli is at 40. Right? There's always a little bit of carbon dioxide, the residual carbon dioxide there. However, that's still a higher number inside than outside. So that difference will cause the diffusion of the carbon dioxide into the alveoli, which will be eliminated during expiration. So notice the oxygen moves in and the carbon dioxide moves out at the exact same time, and they ignore each other's pressures. And that's what the partial pressure of Dalton's law really means. Okay? So that's pretty cool. I like that. That's a really neat concept to know about. Now, we can also look at what happens once we load the blood and pump it down here to our tissues. So now we have blood entering the tissues at 104 millimeters of mercury of oxygen and only 40 of CO2. Well, look at the tissues. The tissues are low on oxygen because they're using oxygen in order to make ATP, for example. So they've been using oxygen up. The oxygen is going away. So they are around 40 or less. So which way does the oxygen want to move? It wants to move from high to low, so out of the capillaries of the blood into the tissues. And remember, it actually goes out of the capillaries into interstitial fluid for a moment, and then it goes into the tissues. All right? And so it'll do that until it goes down to about 40. So it takes most of this and it kind of equalizes again. But look at the CO2. It's producing CO2 as it does aerobic respiration. Remember, CO2 and water are our waste products there. So we're above 45 millimeters of mercury, and we only have 40 millimeters of mercury here. So the CO2 leaves because the higher pressure moves to the lower pressure, and now we have deoxygenated blood that will go to our heart, and we'll start the whole thing over again. All right, so let's underline a couple things there and make sure we understand it. So internal respiration occurs at the tissues. Let's do it in a different color. We'll do it in blue. All right. This is the exchange of CO2 and O2 at the tissues, between the blood and tissues. So capillary blood is 104. Tissue cells is only 40. That means oxygen will diffuse out of the capillaries through the interstitial fluid into tissue cell, leaving the oxygen in the capillary till it gets to about 40, till it equalizes. CO2, the tissue cell pressure is 45. In the capillaries, it's only 40. That means that it'll diffuse from the tissues out through the interstitium into the tissue capillary, and the pressure will go up to about 45. The blood is pumped back to the heart. It starts all over again. All right, so what are a couple other things that help with the diffusion of these gases? So obviously the pressure gradient is one really important thing. When we're at high pressure, we move to low pressure if we can. There's two other things. One is gas solubilities. Carbon dioxide is 20 times more soluble in blood plasma than water is. This helps the diffusion of the carbon dioxide, even though the gradient is really small. It was 45 to 40, only a 5 difference. But because it's more soluble, it will move from the air into the blood, and from the blood out into the tissues and back, or excuse me, from the tissues out to, let me re-say that. Carbon dioxide will move from the blood out into the air very easily, and will move from the tissues into the blood very easily because of the solubility. Think of carbonated drinks. The carbon dioxide bubbles that you're drinking are soluble in the water. They are actually in the water, and you taste them when you drink. All right, so that you can't pump that much oxygen into water. The oxygen will bubble right out again. So the gas solubility helps the carbon dioxide. The other thing that helps both of them is the surface area. And the total surface area is about 140 meters squared. And this is a lot more times than the surface of the skin. This is of the lungs. This is the surface area of the lungs. And I thought, 140 meters squared, I can't even wrap my head around what that means. So I remember I typed in, you can do this if you want, go to Google and type in 140 meters squared and see what comes up. And what I was getting is, think of those big tents, those big white tents that you often will rent out for like a reception for a wedding or a graduation, that are really big and can hold many, maybe 20 or 30 round tables. That's 140 meters squared. That means that all the alveoli, if I were to take them and lay them on the ground and put them next to each other in a big, long, rectangle, it would be about 140 meters squared. So that helps gas exchange occur very fast for us. Now, one last thing before we get into transport of the respiratory gases by blood is this concept, ventilation perfusion coupling. What does that mean? Well, what this means, ventilation perfusion coupling, is that lying all over the alveoli are countless capillaries, and enough where you can get about a liter of blood participating in gas exchange with that 140 meter squared alveoli space that we just talked about. And so any air that is in the lungs, we want to basically match the amount of air reaching the lungs as the amount of blood that can take it, right? If you don't have enough blood going there, then even if you have tons of air in your lungs, you can't pick up enough. So if you had, say, pulmonary hypertension and you didn't have enough blood going into your lungs because of hypertension, constriction of vessels, things like that, you might not get enough oxygen. Or let's say you are having trouble breathing and getting air in, you're having trouble with ventilation, well then you don't get enough air in even though you have plenty of capillaries to pick up that oxygen. So the amount of gas, air reaching the lungs and the blood flow over them must be matched, because otherwise we're going to have troubles. Now, the last thing, I guess there's two things we're going to talk about, is transport of respiratory gases by blood. Now, I often, if I'm doing this in person, I will spend time and I will fill out this entire thing and I will walk you through step by step. I don't think that would be a good use of our time here, because we can just bring up the picture and I can point at things and talk about stuff that way. So I'm going to leave this blank for you. All right, but let me explain to you what it is really quickly and where you can find it so you can follow along. And I'll bring up the picture and you can see the detail. Okay, give me one moment here. I'm going to bring up the page. Okay, it's on page 851. All right, page 851. And on page 851, these are all filled out. These arrows are here, but there's actually things in between them all. So, but real quickly, what I will say, these are the tissue cells of the body. So actually, why don't we call them body tissue cells, all right? And then this is interstitial fluid. And then this is blood plasma. Okay. And then here we have an alveoli. I'll put it down here at the bottom. An alveolus one. A little bit of interstitial fluid, IF. Or no, I lied. That's not. That's the basement membrane right there, the basement membrane. And then we have our blood plasma. Okay. All right. Now, I'm going to pause for a second. I'm going to bring up this thing on page 851. Okay? So hold on one moment. Okay, I'm back, and I've put this here on for us to look at. Now, what I would like you to do, and what I'm going to do, is I'm going to start writing things on the pages of the notes, and then I'll come back and show you where those things are. And maybe what we can do is we can even do it in color. We'll highlight, and then that way you can kind of follow along. So why don't we kind of do the traditional thing? We're going to talk about oxygen first. So we're going to do it in red, all right? But I want a lighter red than what I usually have here. So let me get a much lighter red, almost a pink. Okay, so I think we're going to use that color for oxygen. Okay, and then we'll get, for carbon dioxide, we'll use blue, a light blue in a minute. All right, so the first thing we want to do is look at the different ways that oxygen can be transported through from the alveoli to the blood, and then out of the blood into the tissue cells. Now, you know a little bit about this already because you know about hemoglobin. So there are two ways that oxygen can be transported. One is bound by hemoglobin, and the other is dissolved in plasma. So almost all of the oxygen, about 98, 99% of it, is bound by hemoglobin. And this is because, remember we said it doesn't dissolve very well in plasma. Only about 1.5% of all the oxygen you take in is just sitting there in the plasma dissolved in the liquid. All right, so that is important. Now, a couple other things before we go too far here on the next page. We want to remind ourselves about hemoglobin. So hemoglobin's got our globin protein and heme pigment. And there are 4 hemes. There's 2 alpha and 2 beta chains. Those are the globins. There's 4 hemes in the center of them. And each of those hemes carry have an iron atom in the center of it. All right. And so each can combine with 1 molecule of oxygen. Now, if there's at least some oxygen attached to hemoglobin, we call it oxyhemoglobin. And if there is if there's no oxygen attached, we call it deoxyhemoglobin. Okay? Now, let's talk about how hemoglobin and the pressure of oxygen are related. If you have a lot of pressure of oxygen, high oxygen, hemoglobin will bind with many oxygens and in fact may be completely saturated. Now, you may have had your sat oxygen level taken before, right? And what's happening there is that's where they will take a little clip and put it to your finger, and they will measure. There's a little light that shines through, and they will measure the amount of hemoglobin saturation by the wavelengths of light that they're getting back, that they're recording. And some phones these days even can do this. I'm bringing my phone out right now, and I'm about to show you something. Let's see here. Give me one moment. I think it's under. Okay, so this is my phone, and you can see it says, place your finger on the sensor. And so if I take my finger here and put it on the sensor, you're going to notice, if you can see it, there's a little red light there that just went off. It doesn't like it that my finger's not on it. And then what it's asking me to do is not move. And it's going ahead and it's checking my pulse or heart rate. And it's also checking my oxygen saturation. Now it takes a little time. That's 40% done. We've got to wait a little bit. And it's done. Okay, and hopefully you can read there. It says that I have 79 beats per minute, which makes sense because I have some coffee on board and I'm doing a lecture. And it says 98% oxygen saturation. Now, is this a super accurate one? No, it's not super accurate. However, I can use it to look at, I can use it to kind of look at things over time. And if my values were low and they normally were not that low, that might tell me I should get something checked out. So am I at 100% saturation? Well, it says that I'm at 98%. That's pretty good. Most people are going to be around 98, 99 saturation, okay? If you have low saturation, low pressure of oxygen, the hemoglobin may only be partially saturated. This usually is considered like 95% or lower, okay? And if you're at 90% or lower, you're usually considered hypoxic. So hypoxemia. All right, so I was fine. I'm 98. I'm right in the normal range, between 95 and 100. All's good. Okay, so now the affinity or attraction of hemoglobin for oxygen varies. And what's happening is the oxygen and the heme, the iron part, are attracted to each other. And under certain conditions, that attraction can get greater. Okay, so it varies with degree of saturation. So that's the first thing, is actually the more saturated you get, the greater the affinity. So it kind of helps. It's almost like a positive feedback loop in a weird way. Like as you saturate more and more, the affinity gets greater and greater and more oxygen saturates. So that's good. The other thing is there's a couple other things that will increase or decrease affinity. So let's look at temperature and let's look at pH. Okay, so let's go to those next. So if your body temperature increases, now within limits, of course, like let's say you're exercising, your heart rate goes up, you're producing a lot of ATP and a lot of waste products, and you're not efficient, so your body temperature goes up. Oxygen releases from hemoglobin in where there's very warm temperatures, so the affinity goes down. So why would this be? Well, think this is a good thing. If there's work happening and metabolic reactions, as I said, there's heat production. If there's heat production there at that muscle, then we want to unload a lot of oxygen because these cells are very active and working, and we want to be able to get more oxygen to them. So this is a good thing. This example here is a good thing that would supply active cells like in our muscles. So that's interesting that temperature reduces affinity, meaning that oxygen wants to release from the hemoglobin. pH does the same thing. If we have high acidity somewhere, oxygen gets released more rapidly from hemoglobin. And I want to talk about an effect here called the Bohr effect and the Haldane effect, but I want to show it to you on the next page. So I think I want to do this, but I'm going to show it to you on the next page. But before I go there, let me talk about this last thing at the bottom, and then we'll go to the picture, and then we'll come back and talk about this. There's one other thing here. Hemoglobin at 2,3 BPG, which is biphosphoglycerate. Sometimes it's DPG, diphosphoglycerate. Same thing, means 2 phosphate on there. It's an intermediate compound. This is not shown in any of the figures we're about to do, so that's why I'm adding it in. It's an intermediate compound formed in red blood cells during glycolysis, which is during ATP production, right? So this is, if we're doing a lot of glycolysis, a lot of aerobic respiration, we're going to make this 2,3 BPG. And what it does is it actually combines with hemoglobin and it alters its structure to release oxygen also. So this is another way to release oxygen when we're doing a lot of aerobic respiration. So all three of those release oxygen when we have high temperatures, when we have high acidity, which means low pH, and when we have a lot of intermediates of aerobic respiration. All of those things will release oxygen to those tissues. Okay, now we're going to come back to this, but let's now go and look at what we were just talking about. Okay. Okay, so let's look here. Now the one thing about this picture, and we're going to zoom in, I'm going to start here at the lung actually, is you don't actually need to memorize both of these pictures because they're opposite of each other. So if you know one of them, you basically know the other one. You just have to reverse all the arrows and reverse a couple of the words, and you're good to go. So let's look here for a second. Here are two ways oxygen can go into the blood plasma. So here we are in the lung. Deep breath. Oxygen is exchanging in. 99% of it goes in and attaches to hemoglobin, HB. Okay? 1.5% dissolves in the blood plasma. These arrows give you the relative amount of each thing. So isn't that good? That's kind of useful. Now we know when we see it, we're like, oh yeah, most of the oxygen goes into the hemoglobin. Now look what happens when it goes into the hemoglobin. Look what is on the hemoglobin. There's an H right there. That's a hydrogen. That H gets kicked off. Okay? This H gets kicked off and the oxygen binds. So when we have high PO2, high oxygen levels, we will release this hydrogen. Now, we don't normally like hydrogen very much, right? It makes acidic compounds for our body. But in this case, we have a place where we can use it. And we'll get to that in a minute when we get to the carbon dioxide. Notice it's going up to work with the carbon dioxide. Okay, so that is how oxygen gets in. Now, notice here, the exact same thing, oxygen is going to be leaving the hemoglobin, leaving the blood plasma, going into the tissues. Oxygen on the hemoglobin dissociates off of it and goes to where we have low oxygen. 98.5% of it goes into the interstitial fluid and then goes into the tissues, which are using a lot of oxygen. A little bit of it gets dissolved into the blood plasma and does the same thing. Notice that when we free up this hemoglobin, we now have a hydrogen that we can grab onto and hold onto it, which seems like a good thing because we don't like hydrogen all the time. All right, so those two things are the Bohr effect, all right, and the Haldane effect, all right? So this first one is called the Bohr effect. The Bohr effect is when the hydrogen, a hydrogen will bond to the hemoglobin and release the release the oxygen, out and bind, okay? So if we have a lot of this, a lot of acidity, this will bind to the hemoglobin and release the carbon dioxide. And remember, that's okay because usually where we have a lot of acidity, we want oxygen. Did I say carbon dioxide? I want oxygen to leave and go away from the hemoglobin. This down here is the Haldane effect. As more oxygen builds, we have such a high amount of oxygen, it will kick off the hydrogen and the hydrogen will leave. So this one is called the Haldane effect. So in your notes, you can write Haldane effect over here. You can write Bohr effect up here if you want. So let's go back to our notes and highlight that. So the Bohr effect, hydrogen protons bind to hemoglobin, altering its structure, causing the release of oxygen. The affinity for oxygen goes down. And that's the top one, the one that's happening at the tissues. In the Haldane effect, as more oxygen binds to hemoglobin and alters its structure, hydrogen ions are released, right? So their affinity goes down. And it says ultimately CO2 can be made and expelled from the body. We're about to get to that. We haven't done that yet. So, one thing to note here is during muscle contractions, if we make lactic acid, that will lower the pH, meaning that we have a lot of acidity, and that will cause acidic conditions, which means an increase in free H, right? A lot of this, and that will allow oxygen to be released because more of that will bind to the hemoglobin. All right. We'll come back to this now when we talk about carbon dioxide because we have to figure out where does that hydrogen proton go? Where does it leave? All right. Carbon dioxide is actually a little more complicated because there's not two ways, there's three ways, and in a weird way, four ways that the carbon dioxide can move around. So let's go through those. Okay, so here's the 3 ways. 1, 2, 3. First, and we're going to do this in a different color now. We're going to do it in a light blue color. I'm going to do it in that color. Okay, so carbon dioxide, some of it dissolves in plasma. And remember, we said it's like, 20 times more soluble. So we have about 7 to 10% of carbon dioxide dissolving into plasma. So it just goes into the liquid, and then when it gets to the lung, it diffuses back out due to pressure differences. Very easy. If we go to our notes, you can see that very well here. Let's watch the carbon dioxide leaves the tissue cells, goes into the interstitial fluid, and just goes right into the dissolved plasma. Nothing happens. And then on the way back out the lung, the dissolved plasma just goes right out into the lungs. So that one's super easy and easy to understand. The second one is that we can bind carbon dioxide to hemoglobin, but it's chemically bound and it combines with the globin, not with the heme. And so if it combines with the globin, we call it carbaminohemoglobin. Isn't that interesting? Carbaminohemoglobin. Now this is directly the result of oxygenation of hemoglobin as well, and we'll get back to that in a minute. So let's look at that one. Okay, so here's, let's start down. Oh yeah, we can start here. Here's the tissues producing carbon dioxide. It goes in interstitial fluid. It goes in. If there's hemoglobin available, and there might be some because we got rid of oxygen, any hemoglobin that's available, it'll bind to the globin portion, not the heme portion, but to the globin portion, and it'll form carbaminohemoglobin. And it will float around in the red blood cell, and it will get to the alveoli, and it will dissociate because of pressure differences. Low carbon dioxide here, high carbon dioxide here. It'll dissociate off. And now that hemoglobin can be used by oxygen. Okay? So that is the second way. So those 2 ways are pretty easy to understand. The most complicated one is the last one. And this is by a bicarbonate ion in the plasma and bicarbonate ion in the red blood cell itself. Okay? So this is where there's kind of 2. So this is the bicarbonate ion way. 70% of all of the carbon dioxide goes this way in the bicarb. So we use what's called the carbonic acid bicarbonate blood buffer system. And if you remember looking at that equation below in lab a couple weeks ago or last week, now we're going to talk a little more about it. Okay. So what happens is carbon dioxide enters the red blood cell, reacts with water. So CO2 reacts with water. And right here where this arrow, double-headed arrow is, there's an enzyme inside the red blood cells. Okay? So this enzyme is carbonic anhydrase. And it is going to act right here. What it does is it forms carbonic acid. And then carbonic acid can immediately dissociate in liquid to its ionic forms, to a hydrogen ion and a bicarb. However, we can reverse this, so we can recombine these and run the equation that way as well if we need to. Now, let's look at that. So we're going to bring this back up. So we're going to go here. So we have, what we're looking at here is this one and this one. These 2 are the ones we're going to look at right here. Here and here. So we're going to start on the inside. Carbon dioxide leaves the tissue cells, goes into the interstitial fluid, goes across the membrane into the blood plasma, goes across the membrane into the red blood cell. Okay? It combines with water that's just in the cytoplasm, and carbonic anhydrase quickly, that's what the fast means, turns it into carbonic acid. That carbonic acid dissociates into bicarbonate and hydrogen protons. Okay? Now, let's talk about that just for a second. Actually, let's go up here and then we'll talk about it. Okay. Carbon dioxide. Goes in. It combines with water. Slowly, there's no enzyme. These two things, when they hit each other, they can form carbonic acid just through a normal process. In my Bio 120 class, we do an experiment where I blow in a straw through water, and the carbon dioxide goes through the water, mixes with the water, and causes carbonic acid to form. Just by me blowing through. There's no enzyme, there's no nothing. But it doesn't happen nearly as fast because enzymes, right, make reactions go quickly. So in this case, that will then dissociate into bicarb and do hydrogen protons. Now, think for a second. There's a good thing and a bad thing that's here. We like bicarb because bicarb can grab onto acidic components and make our blood pH stay normal. We don't like the hydrogen, so we want to get rid of the hydrogen. So there's a couple ways we can do this. So one, if we're inside the red blood cell, we can take the hydrogen and we can combine it with the hemoglobin that we had where the oxygen was, but we just got rid of it, and we can get rid of that. That's good. Now, we want this bicarb out in our blood plasma for that 20-to-1 ratio of bicarbonate to hydrogen. So we usually have about 20 bicarbs for every 1 hydrogen. Okay? We've talked about that before. So we have this go out. But there is a problem here. So when we have a negatively charged thing go across the membrane, we cause a charge to occur, right? We have an imbalance. And we need to bring in a charged particle to balance that out. So we bring in a chloride. And a chloride comes in and hangs out while the bicarb goes out. And this is called the chloride shift. So we get a lot of good things that happen here. We have carbon dioxide. We make an acid, which we don't like, right? Acids are bad for us. We dissociate it into something good, a buffer, bicarb, and a hydrogen proton. We take the hydrogen proton and we sequester it with the hemoglobin. We take the bicarb and we put it out in the plasma where we can use it. We bring a chloride in via chloride shift. Okay? All good. Now, what happens up here? Well, we've already got the bicarb where we want it to be. We like that, right? We have the bicarb where we want it. We have a hydrogen proton. That will cause acidity in our blood. But if we have plasma proteins that we can bind it to, and remember that we have a lot of those anion plasma proteins that have negative charge, we can take one of those and bind it to that and get it out of solution. And so now we have 2 bicarbs here that can help our 20-to-1 ratio stay up at 20-to-1. Super cool. Now, what happens when we're at the lung? We need to reverse everything, and luckily this is a reversible equation. So here, this is slow, but we can grab onto those any hydrogens that are around, any hydrogens we've made, combine it with any bicarb, make carbonic acid, and then dissociate it, and then breathe out the carbon dioxide. And we can run the equation to the left there. We can also do it using carbonic anhydrase again, and now we do what's called a reverse chloride shift, where we take the chloride out and we bring the bicarb back in. And so if we do a reverse chloride shift, this comes back in. When we dissociate hydrogen off the hemoglobin, when oxygen comes in, we have a hydrogen available, hydrogen proton. We combine it with the bicarb. We get our carbonic acid. We have the carbonic anhydrase run it in the opposite direction because it can do both. And it'll dissociate and the carbon dioxide will leave and we'll have water left over. Okay? That's how it works. Now, going back to our notes, that's what this last part says. Bicarb leaves the red blood cell and enters plasma in exchange for a chloride. Negative ions exchange to maintain the charge balance. We call this the chloride shift. And this isn't even shown. We'll just put a little not shown here. Not shown. But we can continue the story, I guess. Whoops. Not. Every time. Doesn't like to be over in the corners here. Not shown. Okay. Chloride enters the red blood cell and combines with potassium ion, forming potassium chloride salt. The HCO3 combines with the sodium, forming sodium bicarbonate. As CO2 arrives at the lungs, processes simply reverse actions to release the CO2 in the alveoli. So that's our reverse chloride shift. Okay? Now, like I said, the best way to study this is not to try to memorize everything on this chart, but is to pick one that makes more sense to you. Does things leaving the blood going into the lungs make more sense, or does leaving tissues going into the blood make more sense? Pick one. Learn all the different ways that things move out of the tissues into the blood, or vice versa, for oxygen and carbon dioxide, and understand if you know the chloride shift. If I asked you a question about the other one, it would be the reverse chloride shift. If I ask you about Haldane's effect, you know if it's the opposite one, it's the Bohr effect. So that's the best way, in my opinion, to study for this. Okay, very last thing. This will not take very long. We're going to just do a little basic stuff. Now, control of respiration. The medullary or rhythmicity area is where we control the rhythm of breathing. Okay? 12 to 15 breaths per minute, maybe on average. All right? And there's two different groups. There's the dorsal respiratory group, and there's the ventral respiratory group. Okay? The dorsal one is going to integrate input from peripheral stretch receptors and chemoreceptors especially. Uh-oh, what's going on? And we'll send information to the VRG. And then this is what generates the rhythm and integrates all the info. What are the chemoreceptors that it looks for? It looks for increased hydrogen protons, right? Because then we need to breathe out more. Increased CO2, same thing. We're producing a lot of acids. We need to breathe those out. Or decreased HCO3. If we have a lot of bicarb, then we don't probably need to breathe quite as heavy. So that's one. There it has neurons for both inspiration and expiration. And this goes through a bunch of stuff that I'm not as worried about, but the phrenic nerve innervates the diaphragm. We know that. And you can read about how it all works, but I'm not super concerned. Same thing with forced breathing. We'll activate that group in the medulla to kind of change things. The pons also has a respiratory center, you might remember. And what it really does is it basically smooths out transitions from inspiration to expiration. So the medulla actually does more about rate and maybe a little depth as well. And then the pons tends to do about transitions and smoothing things out and making the inhalation, exhalation very smooth and work well. Okay? So those are the only things I really want you to know about that, the control of respiration. Know that the medulla and the pons are involved. Know some basics about what they do. That's the whole thing. All right, so we're done with every topic for 232 for this term. Your final is going to be coming up. All this new material you need to study, so the physiology of vessels all the way down is going to be on the exam a lot more than some of the material from the first exam. So study hard in those areas and always contact your instructors if you have any questions, and we'll be happy to go over things with you. All right, thanks. Bye.